if I want the first derivative of f with respect to x, I would write this if I were Leibniz, and I would write this if I were Lagrange. If I want the second derivative of f with respect to x, then Leibniz would write this, and Lagrange would just write this. Okay? Now, what about the first partial derivative? This is where it gets new for you today. The partial derivative of f with respect to x looks like this. And this symbol doesn't really have a name. It looks like a backwards 6. But that symbol just means partial derivative. It's not really a Greek letter very much. Sometimes people say that it kind of looks like a stylized lowercase Greek delta. But as long as I'm on this rant, I will show you the differences. Oh. Here is a capital Greek delta. Nope, there we go. Here is a lowercase Greek delta. Here is the partial derivative, and you can get it just by doing the slash, I guess that's a backslash, and then the word partial in Microsoft Word, and then whenever you hit spacebar, boop, that gives you a partial derivative. And so it's not quite a Greek letter. It's obviously not an English letter. Just, it is what it is. You just have to accept it. But I want to point this out that it's not a lowercase d either. It's, its own symbol altogether. And so whenever you see the little lowercase d, that's the derivative in the traditional sense, like from Calculus 1, where you've got a function where it's a function of a single variable, and you want to take the derivative with respect to that variable. That's the lowercase d part. This is something different. This is the partial derivative. In Lagrange notation, if I want to take a function f of, I don't know, perhaps multiple variables like x, y, and z, and I want to take a partial derivative of this function with respect to x, I would write a tiny little subscript x there. And sometimes we could just write this if we don't want to be obnoxious with the whole argument part. Like, this is basically saying the name of my function is f, the arguments are 3 variables, x, y, and z, and I'm taking the partial with respect to x. But you could do this in shorthand and just write f with a little x next to it. If I want the second partial derivative of f with respect to x, this is how Leibniz notation has it. In Lagrange notation, we would just write this, little subscript x's. But I'm going to write 2 of them to show that I'm taking the partial derivative of f with respect, the second partial, since there's 2 of them. Okay, and then last thing is called the mixed partial derivative. And if I've got a function f with independent variables x and y, then this is how I would write the mixed partial derivative with respect to x and y. And I know we haven't talked about what this means yet, but I want you to know, if you see this notation, how you read this out loud, what it's called. Okay? Now, the partial derivative of f with respect to x tells you how steep is the slope of my surface in the x direction. Let me try to come up with a little picture to look at. Because if I've got a function z equals, I don't know what a nice function is, sine of x times y. So this is a surface and it depends on x and y. Do you notice the grid lines on that purple surface? Those black grid lines that lay directly on the purple surface, some of them are in the x direction and some of them are in the y direction. And if I took the derivative, or I should say the partial derivative, if I take the partial derivative of z with respect to x here, then that's like saying, take this point along the surface, and then if I only walk in the x direction, meaning if I walk along one of these grid lines in the x direction, how steep is that curve only in the x direction? We pretend that y is fixed. In other words, you might think of taking a slice or take a trace of the surface in a plane that's orthogonal to the y-axis. Anyways, imagine y is fixed. You can't move the y-coordinate, but you're trying to move along the surface. Then the partial derivative with respect to x is how steep is that. So that's what I mean. How steep is the slope of the surface in the x direction? You could also say the partial derivative of f with respect to x is how quickly does f change because of a small change in x while y remains constant. And if you want to find a partial derivative, like if I have this function and I want to take a partial derivative with respect to x, pretend y is constant, and take a derivative with respect to x. And if you want to take the partial with respect to y, pretend x is constant, and take a derivative with respect to y. So don't be intimidated at all by partial derivatives, because you already know all the skills. Like here in exercise 2, it says find all first partial derivatives of this function f. F is a function of x, y, and z, and f is the function x squared minus natural log of y plus e to the z power. So when I say find all first partial derivatives, I'm talking about take the partial with respect to x, take the partial with respect to y, and take the partial with respect to z. And what is the partial derivative with respect to x? Two x, yep. Because we are pretending that y and z are constant. This is just going to be 2x. What is my partial with respect to y? Yep. Negative 1 over y. Because we're pretending that x and z are just constants. And then what is my partial with respect to z? E to the z, because we just pretend that x and y are constants. Super easy, right? Yeah, it's not too bad. Find all first partial derivatives of g, where g is the function x squared times y minus z times natural log of y plus y times cosine of x times z. So all first partial derivatives means take the derivative with respect to x, take the derivative with respect to y, and take the derivative with respect to z. Partial derivatives, I mean. So what is my partial with respect to x? Mm-hmm. Very good.
Mine didn't have X.
Would it be minus y sine xz?
You're really close. This would be minus yz sine of xz. So the middle term doesn't contain an x. So the derivative with respect to x of z times natural log of y is just 0. So the middle term went away. In the first term, when I take the partial with respect to x, the y is just a constant, so it just hangs out, right? Derivative homogeneity. And in the last term, the y is just a constant, so it just hangs out, plus derivative of cosine is negative sine, and I have to use the derivative chain rule. And the chain rule says, okay, what's the derivative of x times z with respect to x, pretending that z is a constant, and that would just be z. So the chain rule says I have to also multiply by z there. But that's just how it goes. What's the partial with respect to y now?
First part just be x squared.
Uh-huh.
Minus z for y.
Yeah.
Plus cosine x.
Very good. Last one. What is the partial with respect to z? Negative natural log of y What else for that last term?
Minus xy cosine x.
There you go. Well, yeah, there you go. Minus xy sine of xz. Because remember, pretend that the x and the y's are constants. And then derivative of cosine is negative sine, and then the chain rule says you have to throw a little x in front. But yep, that's how you do it. You pretend that the other variables are just constants, and you only take the derivative with respect to the partial you're trying to find. Does that sound good? Okay, and so hopefully that idea fits your definition of a partial derivative too, where we're only concerned with the rate of change of our function as one variable changes. And all the other variables stay constant. Okay, so what if I ask you to find all second partial derivatives? This is the way that second partial derivatives work. I've got a function f, and I could take the derivative, or I should say I should take the partial derivative of f with respect to x. And then I could also take the partial derivative of f with respect to y. Once I have the partial derivative of f with respect to x, I could take another partial derivative of f with respect to x. And once I have the partial derivative of f with respect to y, I can take another partial derivative with respect to y. And I've got those second partial derivatives. There's also something I can do. I can take a partial derivative of f with respect to x and y. And then I could also decide to take a partial derivative of f with respect to y, and then again with respect to x. And what we're going to find is that as long as these second partial derivatives are continuous, that's actually the same thing. It does not matter the order in which you take the derivatives. If you want to do x first and then y, or if you want to do y first and then x, you should still get the same thing. And this is what we call the mixed partial derivative. So if I ask you for all second partial derivatives, then I'm talking about this. I'm talking about these three. That is the second partial with respect to x, and the second partial with respect to y, and then the second partial with respect to x and y. So, what's the partial derivative of this function with respect to x? Two xy. Huh?
I don't like that product.
You don't like it?
You don't like what?
He doesn't like taking derivatives.
Well, that sucks.
It's not 1.
Minus y over x1.
Maybe. Let me write it down because I can't do it in my head.
There's too many x's and y's.
So here we go. Oops. Stop that, Microsoft. Okay. The product rule is f prime g plus fg prime. And so in this case, this part here is going to be the derivative of x, which is 1, times g, which is natural log of x times y. Right? Plus x times the derivative of g, which is the derivative of natural log, which is going to be 1 over x. So it should be natural log of xy plus 1. And so with the minus sign there, it's going to be minus 1. Does that make sense? Yeah. When you take the derivative of natural log x times y, it's tricky because the derivative of natural log is 1 over x times y, but then you've got to multiply by a y because of chain rule. And so you get the y's cancel and you have 1 over x. And you're multiplying by an x, so you get 1. Connor almost had it, but you forgot about this part of the product rule. Yeah. All right. So that is the derivative with respect to x. Let's do it again, but we're taking now the partial derivative of f with respect to y. And so this time we don't need the product rule.
X squared. Minus x squared over y.
Minus xy.
You go to the registrar later and revoke your Calculus 1 credits.
No.
Okay, so we're trying to take the derivative with respect to y. And I guess I should use the little partial symbol. I'm going to take the partial derivative with respect to y of x natural log xy. So think about this as the x just being a plain old constant multiplier, derivative homogeneity and everything. Then the natural log is 1 over the argument. But then the chain rule says I also have to multiply times the derivative of the inside. And the partial of x times y with respect to y would just be x. And so this is x over y. Alternatively, if you're a big fan of logarithms, if you're, which I assume you are because y'all are teaching high school math, right? So y'all love logarithms. The first part is just a constant, right? Because we're pretending x is constant, so x times natural log of x is a constant. The part that's not a constant is natural log of y, which is 1 over y. But there's a property of logarithms that says this is the same thing. The natural log of x times y is the natural log of x plus the natural log of y. Okay, either way, same answer. Doesn't matter how you want to think about it. Now let's take the second partial derivative of f with respect to x. What is it?
2y.
Now let's take the second partial derivative of f with respect to y. What do we get? Yep. And what do I get if I take the mixed partial derivative first with respect to x and then with respect to y? Or it doesn't matter. You could also do first with respect to y and then with respect to x. But what am I going to get?
Two x.
Minus 1 over y.
Okay. And everybody needs to appreciate how you could start from here and take the partial with respect to y, or you could start from here and take the partial with respect to x. But in your brain, I want you to double check this and make sure that it works, regardless of how you attack it. You got it? Okay. Let me know if you all have questions as we go. But that's the idea. So one thing that always confused me as a student is like, why do we call these partial derivatives? And what would it mean to have a total derivative with respect to x? And the answer to this question is partial derivatives only tell part of the story. If I wanted to take a total derivative of a function f with respect to x, where I notice I'm using the little lowercase d's to indicate this is the total freaking derivative, this is going to be the partial derivative of f with respect to x plus the partial derivative of f with respect to y times the total derivative of y with respect to x. This is what we call a total derivative. I'm going to give you an example of when the partial derivative might be different from the total derivative. That's coming up here in a few minutes, so stay tuned. But what I just wanted to explain really briefly, what this is saying is like, okay, the partial derivative is part of the total derivative. It shows up right there as the first term. The rest of it is saying, hey, this function f is not just a function of x, but it's also a function of y too. So let's also consider the effect that y has on the function f, and not just the whole idea of how y might change and affect the function f, but times the way that x has an effect on y. So anytime I make a change in my x variable, it has this direct route of affecting f through the first term here, and it has this indirect effect on the function f because x might affect y and y might affect f. So we're taking into account both the direct effect of x on f and also this indirect effect of x on f through the variable y. So let me show you how that might look in practice. Suppose you sell ice cream on the beach. Your overhead costs are $1,000 per month. Your variable cost is $1 per ice cream, and you want to maximize your total profit by adjusting your price. So profit is revenue minus expenses. Giving you a free business lesson here. Revenue is the total amount of money coming into your business. Expenses is the total amount of money that leaves your business. Overhead costs means fixed costs. Every single month, there are things you have to pay for at your ice cream stand, and it does not matter what happens during the course of the month. Like, you've got to pay rent to be there on the beach. You've got to pay your utility bills so that you can keep your freezer running. You've got to pay your employees, right? There's certain costs that you always have to pay. Those are overhead costs. Variable cost means it depends on how much ice cream you sell. So variable costs might be like spoons, napkins, ice cream cones, right? Those are all variable depending on how much ice cream you're going to sell. So my profit is a function of the number of ice creams I sell and the price of the ice cream. And it's going to be the revenue minus my variable cost minus my overhead cost. In other words, revenue minus expenses. Where the revenue is the number I sell times the price I'm charging. That's the total amount of money that I'm bringing into the business. And so one question you might have is, okay, how does an increase in price affect the total profit? So price is y. And for one thing, if y increases, that's going to also increase my profit, right? If I charge more per ice cream, then every time I sell a new ice cream, I get a larger profit margin. That means it's going to increase my total profit. But here's another question. Does my price affect the number of ice creams that I sell? Yeah, if the price goes up, what happens to the number of ice creams that I sell? Oh, it goes down. So if I increase my price, there's fewer people interested in buying an ice cream. And since that has an effect on my total profit, the number of ice creams going down means my profit goes down. It's a little bit more complicated. And so the partial derivative, I guess, in this situation is saying, hey, increase the price because that's going to increase your profit. If I took the partial derivative of profit with respect to y, then this is just x, right? X is a positive number. So it's basically saying, yeah, you're going to get more profit if you increase your price. But the total derivative of profit with respect to price is going to be that partial derivative of profit with respect to price plus the partial derivative of profit with respect to the number sold times the derivative of the number sold with respect to the price. And so then what you expect to see is the first term is saying, yeah, price directly affects profit by increasing your profit. But this part is saying price is going to decrease the number sold. So this is negative, and profit depends proportionally on, what do you call it, the number sold. And so if this is positive and this is negative, then the second term is negative. There's a trade-off now between increasing your price, decreasing your number sold, and then how's that going to affect your profit in the end. And so this tells the whole story. Does that make sense? The total derivative is telling us the entire story of what's going on, including any possible interactions between your independent variables. So regular derivatives are easily manipulated. What I mean by that is like, I'll tell you what I mean by that. Consider the chain rule. If I want the derivative of some function f with respect to x, and f is a function that's composed with the function g. What am I thinking of right now? I don't know. Then the way I would write the derivative chain rule in Leibniz notation is the derivative of f with respect to g times the derivative of g with respect to x. And when I say that total derivatives are easily manipulated, what I mean is the proof of the derivative chain rule in Leibniz notation is almost like too simple. Once you understand the derivative this way, you think, hey, that dg in the numerator and the dg in the denominator look like they could just cancel out, and then you've got df dx, right? That's what I mean by that. It's not really misleading at all whenever you write regular derivatives, but partial derivatives don't have that nice property. Like, for example, if I were naive, then the way I might think of the partial derivative of temperature with respect to pressure times the partial derivative of pressure with respect to volume times the partial derivative with volume with respect to temperature, I might think to myself, well, dp dp, dv dv, oh wait, dt dt, that's just one, right? And I don't think you would be making any kind of mistake if these were just regular derivatives. But if you have partial derivatives, you've got to be a little bit more careful than this. With the partial derivatives, the way that this actually goes is we say that the partial derivative of temperature with respect to pressure, we got to look at this equation here, my ideal gas law, and think about it. Temperature is pressure times volume over moles times constant R. And if I'm taking the partial of temperature with respect to pressure, that would be volume divided by moles times R. Okay, what about the partial derivative of pressure with respect to volume? Well, using this, I would say that pressure is moles times constant R times temperature divided by volume. So the partial of volume with of pressure with respect to volume would be negative nRT over V squared. And then the next thing I want is the partial of volume with respect to temperature. And using my gas law equation, I have volume equals nRT over P. And so the partial of volume with respect to temperature would be moles times R over pressure. And now we want to multiply these together. So let's multiply together V over nR times negative nRT over V squared times nR divided by P. Okay, so now we get out our eraser or our red pen or whatever. We start canceling some stuff. What am I not doing correctly? I don't know. Let's see where it goes, and then we'll think about it later. Has anybody seen me make a mistake yet in this problem? I'm only asking because I think that not all of these are going to cancel, and I expected all of them to cancel. So let me go back and really carefully think about this before we move forward, because I really, I'm seeing, for example, just like V divided by V squared is going to give me 1 over V. Actually, screw it. Let's just go ahead. Let's try to solve it. Maybe I'm second guessing myself, and I don't need to be. Let's see what we get before we start thinking too hard here.
Wasn't one to not cancel?
V divided by V V divided by V squared is 1 over V, right? R and R cancel, but I'm left with 1 R in the numerator. This N can cancel with this N. I'm left with 1 N in the numerator. I also have a T, nRT, and a PV, and it's negative. Aha, so I wasn't doing anything wrong. The only thing I did wrong was not believe in myself. If PV is equal to nRT, according to my equation that I started with, that means in the denominator, PV is equal to nRT in the numerator, which means that this is -1. And that's what I wanted to find, okay? So just to recap, the correct solution to this problem is actually -1. But if you were naive and you just tried to immediately start canceling out the partials, this would be incorrect. You'd only get +1. So, isn't that weird? Not just a little weird. Everybody's taken general chemistry, right? You need to. Or slackers. I don't know why you would go to college and not take general chemistry. It's like, I don't know.
Yeah, I think it's like not required for almost everybody in here.
Yeah, but just because it's not required, you're not going to do it.
Whoa, whoa, whoa.
All right, whatever.
It's not an overly exciting class.
Oh, you were a chemical engineer, right?
Yeah.
Oh, that's right.
Yeah, that's why he said
Okay. Does anybody have any questions about this? The point of this example is just to show you that partial derivatives, they don't always behave well. Sometimes you get some minus signs popping up, and it doesn't really seem like it should work, but it does. Okay. You learned about implicit differentiation in Calculus 1. It works a lot differently in Calculus 3 when we have more variables. So you can forget everything you learned in Calculus 1. Instead, we're going to do it like this and say, if you have an equation where the left side of the equation is a function of both x and y, and the right-hand side is just 0, then if you want to take the derivative of y with respect to x, it would just be negative capital F subscript x. Do you remember that's the partial of f with respect to x, divided by the partial of f with respect to y. But it has a little minus sign there. That's kind of the confusing part. I'm going to rewrite this whole thing in Leibniz notation so I can show you why I'm always confused by partial derivatives here. Except there's a minus. I forgot the minus. That's the most important part. So if you subscribe to the idea that like dividing is the same thing as multiplying by the reciprocal, then you would say, well, partial f over partial x times partial y over partial f would have the partial f's cancel, and then you would have this weird situation where, you know, dy dx is equal to negative partial y partial x. Doesn't really make sense. But keep in mind, partial derivatives are not easily manipulated. You can't just do it the naive way. We have to be more careful about how we do this. And then this is the extension for what does it look like if I have a function of 3 variables on the left-hand side and 0 on the right-hand side of my equation. Well, then it looks like this, to take the partial derivatives of z with respect to y and so on. All right, so proofs. Let's begin with this one. I want to prove that if I have some function, I'll make it capital F to be consistent. If I've got some capital F function of x and y, and I set this function equal to 0, that this is true for implicit differentiation formula. If I have capital F of x and y, maybe I start off by deciding I'm going to take the derivative of f with respect to x, and not the partial derivative, but the total derivative of f with respect to x. And like I showed you before, that's going to be the partial of f with respect to x plus the partial of f with respect to y times the derivative of y with respect to x. Now, what I actually want to prove this formula is true is I need to find dy dx by itself, and it's right here what I want to have isolated, so I just need to rearrange this a little bit to isolate that. Maybe the first thing I should note, though, is that if this function is identical to 0 for every valid choice of x and y, then the change in f with respect to anything is 0 because f is 0. It's a constant. Right? For any valid choice of x and y that satisfy this equation, the capital F function is 0. That's what it means to satisfy the equation. So if capital F is always 0, it's a constant function, and that means any derivative of a constant function is 0. So I can use that knowledge over here and make this into a 0. And then the rest of this is just kind of algebra. And then I'm going to divide by the other one, so it's minus this divided by this. And that's what we were trying to prove. So what am I looking at? I've got this big equation, and it's got x's, and it's got y's, and it's got z's. It's got a lot of stuff going on. In order to use my implicit differentiation formula, I need the left side of the equation to look like some function of x, y, and z. And I need the right side of the equation to be 0. So let's rearrange this equation here. So that the right-hand side is 0. And then we need to use our formulas, which say the partial of z with respect to x must be the negative partial of f with respect to x divided by partial of f with respect to z. And f is the whole left side of the equation. So what is the partial of f with respect to x? Yep, 6xz. Yeah, that's a squared, that's not a z. Okay, and then what is the partial of f with respect to z? That's it. All right, so that is the partial derivative of z with respect to x. And we can do that even though my initial equation wasn't defined explicitly, where z is a function of x and y. This is an implicit equation, but we can still do implicit differentiation on it to answer these questions. All right, we got 5 minutes left. Let's do one more. Find the partial of z with respect to x and the partial of z with respect to y for this relation. So the partial of z with respect to x is going to be negative partial of f with respect to x divided by partial of f with respect to z. And the f function for us is going to be z minus e to the x times sine of y plus z. So what is the partial of f with respect to x? Remember, we're pretending that y and z are constants. So sine of y plus z would just be a constant multiplier, so it goes along for the ride. And then take the partial of capital F with respect to z, and we get 1 minus e to the x times cosine of y plus z. Don't need to use product rule because e to the x is a constant, remember? So easier than you think. And that's the answer. That's the partial of z with respect to x. If I have the partial of z with respect to y, that's just negative partial of f with respect to y over capital F with respect to z. Because the way we name variables is completely arbitrary, right? You could name it something else if you want to. Name x, y, and yx, and it should still work.